New crazy model 1 hour ago. Look at this. There is new image generation model. Look how it works. It's crazy. I like it. From the beginning, it goes like this. They published research paper. We will go into technical details and everything we will understand. Model is open source on Hugging Face. They have breakthrough in AI image generation, and let's see how it works, and they're using continuous tokens. Imagine you're trying to teach a computer to create images from text descriptions. Currently, there are two main approaches, both with significant drawbacks. Diffusion models. These are powerful but computationally expensive, like using a sledgehammer to crack a nut. Vector quantization models. These convert images to discrete tokens, like Lego blocks, but lose quality in the process. So Lego just turns continuous image data into discrete tokens because there is infinite or almost infinite number of possible images, so it's continuous data. You change one pixel a bit, it's continuous data. It's not like large language model where you have certain tokens, it's discrete tokens, and there is like 200,000 and that's it. And there is like billions images, possible images. It's almost infinite. NextStep-1, which is the name of the model, introduces a third way, using continuous tokens with autoregressive generation, combining the best of both worlds. NextStep-1 is a 14 billion parameter AI model that generates image by reading text descriptions, creating images piece by piece, patch by patch, using continuous values instead of discrete tokens, like painting with smooth brush strokes instead of placing Lego blocks. Key innovation, the two-head architecture. Text input, transformer, two specialized heads. Language head for text, flow matching head for images. How does it work? Step 1, tokenization. The model first converts inputs into a format it can understand. Text, discrete tokens, like words in dictionary, okay, so text to discrete tokens. And images to continuous tokens, smooth numerical values. Step 2, sequential processing. Like reading a book, the model processes information left to right. Reads the text prompt, generates image patches one by one. Each new patch depends on all previous patches. Nice. Okay, so just where is diffusion or where is continuous tokens coming in here? Step 3, flow matching. Instead of jumping directly to the final image, the model starts with random noise, gradually flows the noise towards the target image. This is similar to diffusion, but let's see how this works. I'm not sure. Uses a small neural network, 157 million parameters, very small, to guide this flow. We can run this on a single GPU easy. The training is in multiple stages. Foundation is stage 1, 1.23 trillion tokens. Stage 2, resolution enhancement, so bigger resolution, 0.6 trillion tokens. So it just doubles each side, so quadruples number of pixels. And then quality refinement, just 40 billion tokens, high quality data only, aesthetic improvements. And then lastly, we have human preference optimization, post-training. Surprisingly, the size of flow matching head barely matters. The researchers tested 3 different sizes. Small, 40 million parameters, base 150 million, and large 500 million parameters. All perform similarly. This proves the transformer backbone is doing the real generative work. We just cannot get away from this transformer, it seems. Tokenizer design is critical. The image tokenizer includes special features to prevent common failures. Channel-wise normalization prevents artifacts at high guidance scales. Noise regularization creates a more robust latent space. So I guess this would have like some noise and then normalize it or regularize it somehow. High reconstruction quality. This is a measure of something, I guess. So I just want to mention that I think the future is not in tokens, it's in direct raw bytes. But for that we need to, like transformer cannot work with raw bytes because there is a lot longer sequence of raw bytes. But we want to have AI models that take bytes and output bytes directly. But there will be also these token level AI models and stuff. I think there will be like all kinds of models. Let's see continuous versus discrete tokens. Unlike traditional approaches using discrete tokens, like choosing from a fixed palette or dictionary, continuous tokens allow smoother gradients, better detail preservation, more natural image generation. So how do these continuous tokens even work? Discrete tokens, traditional approach, think of discrete tokens like a paint by numbers kit. Let's just understand discrete tokens because this is also used in other models and there could be models in the future with this. And we will understand easier the continuous then. So we have 16 times 16 combinations of pixels image. So we cannot actually, in this token, we cannot store every possible combination of pixels. It will be almost infinite. Almost 2000 zeros here, 2000 numbers. There is 10 to 80 number of atoms in the universe. This would need so many universes. What discrete tokens actually are, the codebook system. Instead of all combinations, discrete tokens use a learned codebook. Think of it as a curated library of the most useful visual patterns. The codebook analogy. Imagine you are creating a mosaic. So instead of every possible pattern, we have, let's say, 8,000 common tile patterns. So pattern 0 is solid sky, a solid blue sky. Pattern 1 is grass texture. Pattern 2 is skin tone gradient. And then a wood grain, cloud wisp. And lastly, metallic shine. How vector quantization works. Step 1, building the codebook training phase. So first we initialize this dictionary, let's call it, or codebook. There is 8,000 something possible these patterns, and each dimension is 256, so 256 numbers to represent. It's like tokens in large language model. Then we take image and we convert that to continuous numbers with some encoder. It's gonna have some linear layers project. And then for each patch, we find the closest possible patch from this codebook, the closest vector. So find nearest patch of the image and the codebook. And then we will update codebook to better represent common patterns. So we will learn from this actual patch in the training data and update this codebook patch to better represent this actual patch. So we will just have, in this codebook, we will have representations or most common patches of the real data. How images are tokenized. So we have an image and we divide it into 16 into patches, let's say 16 by 16 pixels each patch. Then all of the patches are encoded one by one into some vector, and then we have these tokens. So for every patch, which we call features, now they are features because now they are encoded vectors. They are no longer patches. We find the distance to the codebook, every vector, and then take the minimum of those distances. So closest ID from the codebook, closest vector. And then tokens, we append that closest vector, or closest ID, I should say, of the codebook. Real example, how a cat image becomes tokens. So we're gonna go from original image to discrete tokens. So cat photo, 512 times 512 pixels, split into 32 times 32 patches. So it means each patch is 16 pixels with height. Then each of those 32 times 32 patches is compared to a codebook, but first it's converted to a feature with some linear layer or encoder or a few linear layers. And then that feature, that representation of the raw patch is compared to every codebook vector. So maybe patch 00 looks most like code 2451, for example, orange fur pattern. The other patch looks like orange fur, slightly darker, then this patch looks like maybe green center of the eye, and then this patch looks like edge of the green eye. So then we just concatenate these entries from the codebook. Look how they go. So these are indices for now. We just concatenate indices of the entries. What's inside each codebook entry? Each codebook entry is not a literal 16 by 16 pixel image. Instead, it's a learned feature vector. So let's take an example for this first one that's maybe a pattern of orange fur. It's just a vector, like a token embedding for large language models. And each of the dimensions could represent something. So first dimension could represent orangeness, second furriness, third horizontal texture, brightness, edge strength. There could be dimension that represents how much this looks like an eye. So that dimension number in this case would be low, because this fur texture, if this is fur texture, then doesn't look like eye so much, so that dimension number would be like close to 0. But that same dimension for this green eye entry would be strong, maybe close to 1 or above 1. We can see here that they can go above 1. They're probably very close, around 0, so around 1 minus 1, but not too far away. These so they are stable and don't explode when we multiply them with weights. These features are learned automatically during training. We don't manually decide what they represent. They're going to learn to represent things that are going to get us lowest loss. So that are going to have when we train, we're going to get the closest thing to the data. We're going to generate data with it. This is how AI can learn like random things we can't even imagine, because these features probably can represent some concepts that we cannot even imagine. Especially when you look at these 3 features combined or something, or the whole vector even. But whole vector maybe we can visualize. I want to show you a prompt for this, how to write these nice explanations. Explain this step by step. Write markdown article that is easy to understand. So step by step and markdown article that's easy to understand. The critical trade-offs, cookbook size examples. We have all of these models, and they have 512 codes, 8,000, 16,000, 1 million. This is hypothetical, 1 million codes. This doesn't exist. So these are modern. I guess these are good. And then all combinations is like too big number. The more you increase codebook size, it says here better quality, but maybe not. Maybe we can get smarter ways of doing this, so we don't need to increase just size. It's codebook, not cookbook. This is the quantization process, very simple. We have some vector. We calculate distance to each of the vectors in the codebook, and this one is closest, and then we save ID of this vector. But there is some lost precision here, you see, a bit of lost precision, but that's okay. So there's the fundamental limitation, quantization error. So this is the thing that gets lost is the problem. Unique textures are replaced with the nearest common pattern. Fine details approximated or lost, rare visual elements forced into common patterns. Why not just use more codes? The scaling problem, it's scaling kinda quadratically, exponentially. It's not scaling linearly. And now it's easy to understand these new continuous tokens. So they are the actual feature vectors themselves. No codebook, no IDs, no quantization. The feature vectors that we got in the beginning. Step 1, image to continuous latent space. So we have 500 times 500 times 3 RGB image. Output in this variational autoencoder is 64 times 64 times 16 continuous latent. So it's just some tensor that has these numbers, and inside each number is some number. And then we have this key innovation, which is normalizing for stability. We calculate some mean and some standard deviation, and then subtract mean divide by standard deviation. We'll see later better example of what we calculate mean and standard deviation. But this normalizes it, so it's gonna be at mean 0 and standard deviation 1. We have some slight noise addition for robustness that prevents overfitting. So noise scale is random between 0 and 0.5, and then we add latent plus noise scale times this noise. And in the end, we will convert our 3D tensor into 2D tensor that has 1024 entries. Each entry is 64-dimensional vector. Similar to this dictionary, where you just have 1024 rows, each row is this 64-dimension vector. We will learn more about this. Key insight, the 16-channel latent space. The variational autoencoder learns to compress images into 16 channels. Here in the beginning, it goes from 3 channels red, green, blue to 16 channels, and height and width are reduced because each of the channels will learn some unique feature like edges or circles or to something. This is hypothetical learned channel meanings that are automatically discovered during the training. For example, overall brightness, red-green color gradient, blue-yellow color gradient, vertical edges, horizontal edges. And then we can have some complex learned patterns that maybe we cannot describe so easily. How continuous tokens flow through the model. The autoregressive process. Let's see generate image that gets text prompt. First, process text into context. So we have tokenized text, so we get text tokens, and then we pass text tokens through the transformer. And then inside of that transformer, it gives us some hidden states. And then we will generate continuous image tokens one by one with that transformer. Starting from nothing, there is 1024 positions, so we're gonna generate 1024 patches. Get context from all previous tokens. So we get context from text tokens, image tokens up until this position. I would guess they're using cross attention here to get text tokens and image tokens, but we'll see. And then just generate the next continuous token, which is this 64-dimension vector, using this flow matching head.generate and passing context and position. We need that. And it gives us next token. So we'll learn more about this flow matching head. And then append next token to the image tokens. In the end, we take those 1024 vectors of each length 64 and we convert that to the image. No, to the latent 64 times 64 times 16, so 16 channels. So that's our latent for the whole image. So we just now converted sequence of patches to a latent for the image, and then variational decoder, we convert the latent of the image into the actual image. Just to recap, first we generated 64 vectors one by one, 1000 of them, 1024. Then we convert that 2D tensor into a 3D tensor, and that 3D tensor is gonna be our latent representation of the image. And then we convert the latent representation of the image into the actual image. Flow matching head, where the magic happens. This is the key innovation. How do we generate continuous values autoregressively? The problem? Discrete. Next token is 2451. Easy. Just pick from 8000 options. Continuous. Next token is, and then we need to generate whole token. There is infinite possibilities. The solution, flow matching. Instead of directly predicting the 64 values, we learn to flow from noise to the target. So this is similar to diffusion. But I'm not sure how exactly. Let's see. So the flow matching head, we already know this generate method exists and it takes the context, which is gonna be text and the previous tokens. And number of steps 10. Let's say this is maybe to generate the next vector. Start with random noise. So torch random, so 64 random values. The context tells us where we want to go. So target direction is equal to self.process context and passing context. We'll see how this is used. So we just process context somehow, maybe with some a latent space or something. Gradually flow from noise to target for step in number of steps, which is 10. This is similar to diffusion, it seems. What's the optimal path from here to target? Now we have this concept of velocity, which I didn't see in diffusion. So velocity is equal to self.predict velocity. We have current position, which is our random vector. Okay, I understand. Let's go. Target hint, target direction, which is our text and previous vectors, and time remaining, which is just gonna be encoding our steps. So the neural network knows how much noise it currently has and how much it should subtract. Interesting. This is such an interesting concept. This is the first time I see this concept, velocity. And then take a small step. So the new vector is gonna be old plus velocity times 0.1, which is similar to a learning rate. But this is different, of course. And then it goes for these 10 steps. And as I understand, it has this vector, it has direction in which it should move, and it has velocity. So it's moving with actual velocity here. And that's it. Interesting concept. So if diffusion is working well with continuous data and autoregressive transformers with discrete data, what is this flow matching thing working well with? Maybe some combination of continuous and discrete, I'm not sure. Or maybe just continuous data. Visualize the flow process. Step 0, pure noise, some random numbers. Step 2, rough reshape. So all of the numbers got a bit different. Step 4, basic features, then refine details, and then fine tuning step 8, and step 10, final token. The mathematical foundation, ordinary differential equation. The flow matching head solves. This is a bit tough to understand. So I think how our vector x changes as time changes. So that's what the equation is trying to solve. And that's gonna be equal to our neural network, which is our learned velocity field neural network. That's gonna get passed in position at time t, which is our vector at time t, the time step t, and the context, the direction. So yeah, so we have neural network, it gets vector at time t, and the context direction. And the neural network is learning how the vector changes as time changes. Then we have this function train flow matching, which is gonna take a real image token and context. We'll see what this is. So first, sample random time between 0 and 1. So we want to train for every time step. So let's sample some random in this case. 2, create noisy version, interpolate between noise and real. So we will just create a random vector that's same shape as the real image token, but the values inside of it are random. And then we're gonna create our noise vector. Now I understand this. So we wanna simulate our vector that has a part real data and part noise, depending on the time step. So the higher the time step, the more it will have of the real correct data, and the less it will have of the noise. And other way around. If the time step is low or 0, then it will have very low real data or 0 real data and very high noise. And we are using this actual real token, real data, real vector embedding of 64 to train this flow matching. 3. True velocity is the straight path. So true velocity is a real image token minus noise. And noise this is our random noise that we generated. Okay, it makes sense for me right now actually. 4. Predict velocity with neural network. Flow matching head, we give it our noise vector, timestamp and context, and that's the predicted velocity. And now we calculate loss between predicted velocity and true velocity. This is so understandable. I can't believe. And if any of you don't understand, maybe you are beginners, don't worry. A year ago, I didn't understand anything, but now I must say, it's so understandable. Because it's very similar to other things. It's so similar to other things, like diffusion and training neural networks. So as you're learning this, you're learning everything else at the same time. Why continuous tokens preserve quality? No information loss chain. So discrete token path, we have original image or token, let's say original token. So we compress and then quantize, and when we quantize, we need to snap to the closest token in Codebook, so we lose some information. So when we decompress, we're gonna decompress a bit different token. But in continuous, we have original, compress, store values, and decompress, so we don't snap to some close original, close token, we just decompress the same token. Gradient precision example, generating a sunset gradient. Discrete tokens, limited to Codebook entries, but continuous tokens. It can have exact orange shade, it can have smooth transitions. Then we have advanced features of continuous tokens. Interpolation capability, so can smoothly blend between two images, token A, or let's say encoded image A and encoded image B. We can create smooth morphing, where we just take 0% or 1/4, 1/2, 3/4, and 1 full of the first image and combine with the other image, and that's how we blend. And we do that in latent space, and then we decode blended. Continuous tokens support semantic arithmetic, so we encode sunset, image of a sunset, ocean, and desert, and then we say sunset minus ocean plus desert, we're gonna get sunset desert, and in the latent space, and then we decode sunset desert. So we just subtract these vectors, actual numbers, latent space vectors. Fine control, adjust specific aspects precisely. We have, for example, some tokens for brightness or contrast, but how do we know which ones are for which? I'm not sure right now. Maybe we can just try, test, and see which ones are for which. And maybe once we test it once, it's same for every image, I think. The normalization trick, why it's critical. Later tokens in the sequence can have these big numbers because they multiply with each other and take context from each other and multiply with weights, with everything. So the numbers can explode, which is not good. Now they're drifting away just because of multiplication, so we need to normalize each one. So we have this channel-wise normalization. Each channel forced to standard distribution. This is a bit confusing for me, but as I understand, they take first channel and first channel of every token, and then take mean and standard deviation of those. So not of all of the numbers in the token, but just per channel. So first channel of every token, and then normalize that, and then second channel and third. Then we can go back, look some funny images, and we have this freeform manipulation. Interesting. Image editing. This is what it looks like. Beginning of sequence, dog on rock, and then image of the dog on the rock. We have causal transformer that takes every token, text token, and we have this image tokenizer that also puts image tokens into the causal transformer. So we have beginning of image, end of image, and in between these patches. So we have LM head, as I understand this is for text, and flow matching head, we know that that's for tokens, for the next token. Surprising discovery, the transformer does everything. The flow matching head is just a translator, not the brain. The researchers made a counterintuitive discovery that challenges our assumptions. They tested 3 different flow matching head sizes and got nearly identical results despite 13 times size difference. Traditional thinking, transformer 30%, simple head 70%, which means that head does the generation. Actual reality, transformer 95%, and 5% for the simple head, which means the head just converts format. It's not clear to me either 100%, but this proves the transformer is learning the actual image structure, composition, and semantics. The flow matching head merely converts the transformer's understanding into continuous values. Okay, I understand now. Then revolutionary concept 2, chain of thought for images, teaching AI to think before drawing. They have this, instead of generating images directly from prompt, they have this AI thinking. I should create a cat with mechanical elements like gears, brass fixtures, goggles, and then generates a much more detailed and accurate image. There is 15% and 24% performance boost on these benchmarks with reasoning. Insight 3, the art of data curation, the 400 billion token recipe. They didn't just throw random data at the model. Here is their secret sauce. They have 400 billion for text only, a bit more for image text pairs, only 1 million for image editing, interleaved, not sure. So this is complex reasoning, I guess, and character videos, 5 million consistency learning. And for the last 20,000 steps, they only train on the best 20 million images, which I guess means that they have 1,000 images per one batch. Just a random thought here, because one step is one batch unless they do gradient accumulation. Then it could be 500 images or 250 images per batch. So they judge these best images on aesthetics, clarity, no watermarks, performance alignment. It results in massive quality jump in final model. Breakthrough 4, character-centric learning, how they thought consistency. They developed a clever pipeline for video data. So they're gonna process the video, extract faces, it should say detect faces, and then track same person across frames. 3, generate story-like captions. 4, character-in-character tracks. Caption is gonna be equal to generate narrative character.scenes, and this will be something like the man in the blue shirt walks from the door to the window, then turns to smile at camera. I guess they just generate bunch of images that have like same character, and maybe this is for fine-tuning, I'm not sure. They have some ablations and tests on hyperparameters and settings. The problem with autoregressive generation is you generate one by one, so as your image grows, the number of tokens grows quadratically that you need to generate. So high resolution images are gonna be a lot slower. But maybe we can just use like resolution increasing enhancement diffusion model or something after we generate these small things with autoregressive, if it's better. Then for inference optimization, they suggest using speculative decoding, distillation to reduce flow matching to 1 to 2 steps, multi-token prediction, and the importance of data diversity. Too much perfect data gives boring model. Need messy, diverse data for robustness. The meta lesson, simplicity can win. They didn't invent new architecture, just applied autoregression cleverly to continuous values. Small details matter enormously. Channel normalization, 3 lines of code, made the difference between failure and success. We need to normalize channels. Theory is different from practice. Adding noise should hurt quality, but actually helps. The head size should matter, but it doesn't. Scale helps, but isn't everything. The 157 million parameter head performs as well as the 528 million one. Smart design beats brute force. The most important takeaway, the breakthrough wasn't in inventing new technology, but in finding the right combination of existing techniques. Autoregression from LLMs, continuous latents from variational autoencoders, flow matching from generative modeling, normalization tricks from deep learning. Innovation often comes from clever combination, not invention from scratch. It also comes from understanding. They understood how all of these work and then figure out how to combine them. That will be it for this video. Check out my other videos on my channel and where we do research, explain papers, code, learn everything, and see you next time.